Okay, welcome back everybody. We're moving on to chapter 12 here. This is called Surfaces in Flux. In particular, for today, we're going to be focusing pretty strongly on this idea of surfaces. So surfaces primarily we can think about as, the two-dimensional subsets of our three-dimensional space. I'm sitting at a desk right now. I can talk about the surface of the desk is a two-dimensional entity, but it's embedded in our three-dimensional space. I can talk about the surface of my water bottle. Similarly, grab any object and it's going to have a surface, but technically, mathematically, we have ways of talking about these surfaces in higher dimensions even. So really, at the end of the day, a surface is a one lower dimensional piece of an n-dimensional object. Okay, so it's just like, we're in three dimensions, we have a three-dimensional object. If I consider a two-dimensional piece of that object, then that's a surface. Okay, and that's what we're going to focus on today. What's really nice about this definition of surfaces is that it allows us to basically define, maybe I'll mention that up here, this characterization is efficient because we can, I can spell the word can define first the 3D object, then restrict it to a surface. And it turns out that it's a lot easier to just start with the 3D object and then restrict it to the surface than it is to try to come up with some equation for the surface of the object in the first place. So that's kind of the nice idea with this definition. So here's a nice example. The book just starts with a nice example. So this is a three-dimensional object, x squared plus y squared plus z squared. It's the analog to the paraboloid, but in three dimensions. Analog to paraboloid in 3D. So we can't really visualize this because the f that outputs is sitting in the fourth dimension from my three inputs in three dimensions. But here's the idea now, is that if we take this four-dimensional object and we restrict it to a specific value, in this case we restrict it to be equal to 1, we make this definition ourselves, and we say that's going to be the one-dimensional, or sorry, it's going to be the 4 minus 1 dimensional object. In this case, 4 minus 1 being 3, three-dimensional object of x squared plus y squared plus z squared equals 1. And that's exactly what we call a sphere. So here it says gives us a spherical surface. So we have a surface, which is technically three-dimensional, that arises out of a scalar function with 3 inputs, and then we restrict the scalar function to a specific value. So we're jumping back to level curves, right? So all of these level curves you were interacting with earlier, we're giving you objects like this. And we just want to, start studying them a little bit more concretely. Okay, I'm going to skip that because it says, however, we will not need such abstraction, because we really do not. So what we want to think when we have these surfaces is that we can define them what's called implicitly. So when we do this level curve definition, that means we define them implicitly. And what does implicit particularly mean? Implicit means we don't isolate one variable to one side of the equation. So this is a great example. Notice that both variables are on the same side and both are higher powered than 1. Okay, so this isn't the case of y equals cosine x plus e to the x minus x squared. That would be an example. This is an example of explicit because I've isolated y to the left-hand side. And I have functions of x on the right-hand side. Over here, both x and y are still sitting inside little functions, and they've both been placed on the same side of the equation. So that's the difference between implicit or explicit definition of surfaces. And it turns out that implicit surfaces are very useful because they describe a wider variety of objects than the explicit ones. So we're going to focus on those for now. All right, so this exercise says verify the set of points x, y is indeed the unit circle. That is the set of points right here. Hint, you can take the points to be cos theta, sine theta for theta, and notice that these all live on the circle. So if I plug cos theta in for x and sine theta in for y, I get the Pythagorean identity. So that's how we can verify that. All right, and the author is noting that, yes, this is just like level curves for us. Okay, now we're going to actually look at this sphere, x squared plus y squared plus z squared equals 1 as a level surface. We're claiming we get a sphere from this. Let's actually look at the plot of all possible triples, x, y, and z, which satisfy this equation. The plot looks like the following, and indeed we do have a sphere. Now we should note that this sphere is empty, right? Like it's hollow. So we have a nice three-dimensional object, but it doesn't have an interior. It's like a basketball, more or less. So that's something special about the sphere, is that it's hollow. So spheres are hollow, balls are filled when it comes to mathematics. So the sphere here is a hollow sphere because the point, for example, the point 0, 0, 0 does not satisfy that 0 squared plus 0 squared plus 0 squared equals 1. But if I grab any point on the surface here, let's grab this point right there in the x direction, that's 1, 0, 0. If I take 1 squared plus 0 squared plus 0 squared, I in fact do recover 1. The Wolfram code that you'll be using for implicit surfaces. Implicit surfaces in Wolfram is either contour plot or contour plot 3D. Okay, this is for implicit. When we go explicit, then you can define things differently, but the contour plots are used for implicit surfaces. So if we wanted to plot something like this in Wolfram, we go contour plot. How many dimensions do we have? We have 1, 2, 3 dimensions. We would write that equation in there and then specify our bounds, and it would output a sphere for us. We can restrict the sphere to other values, right? If I took my function x plus y squared plus z squared, all of the elements squared, and I chose a different coordinate or a different constant value here, c, then the sphere would grow or it would shrink depending on how big or small c is. But in particular, if c is equal to 0, then this reduces to a point. And points are no longer three-dimensional. Points are one-dimensional or zero-dimensional objects. And so we lose three-dimensionality exactly when c is equal to 0, and that's going to become very important to us. Okay, I'm not going to go through that because it's not terribly important. But yes, so this is what I was trying to get to with especially when c is equal to 0. If we decide to set c equals 0, or the constant level equal to 0, and I calculate the gradient of my function, let's recall what the function is, f of x, y, z, this is a scalar field, was defined as x squared plus y squared plus z squared. If I calculate the gradient of that, I'm going to recover 2x, 2y, 2z. And in particular, the gradient at the point 0, 0, 0 is the 0 vector. And that's going to be very special. So this idea of having the gradient be the 0 vector is very special. That means that there is no implicit, if I can spell, surface, aka level surface, passing through that point. Okay, because the specific case when c was equal to 0, it became degenerate. Degenerate in the sense that my dimension has collapsed. So the dimension has collapsed to a single point at those specific places. And so if we find a point at which the gradient is 0, which you'll recall is also a local min or max, possibly a saddle point of the surface, you can't actually gain an implicit surface by restricting the function to be equal to a constant for the surface to pass through that point. So that's something just important to keep in mind, and that basically describes if we have the ability to create a surface passing through any given point dependent on some vector. So this can be summed up in the following theorem, which is right here. Implicit surfaces exist if and only if the gradient is non-zero. So if there's a point on this level set for which the gradient is equal to 0, then in fact the surface becomes degenerate. So it drops in dimension around that point. Okay, so let's look at hyperboloids. The reason for hyper instead of para for boloids is just referring to the sign between each of the squared terms. So because we have one negative sign here between at least one of the squared terms, that determines which direction behaves differently from the other two. So we're going to see that in these hyperboloids, the z direction behaves particularly specially as opposed to the x and y directions. And we're going to create a surface by setting this function equal to a constant value. Okay, so taking c equals 0 and setting it equal to 0, we're going to get a surface, but there's going to be, let's take a quick step back and ask ourselves the question, what is the gradient of f at the point 0, 0, 0? Well, the gradient was negative 2x, positive 2x. It was positive 2x, positive 2y, and negative 2z, and at the point 0, 0, 0, that means the gradient becomes degenerate. And so we'll find out that the surface that we recover in this very special case, it exists away from this point, but at the specific point, the surface, we're going to notice that the surface becomes degenerate and collapses. So let's scroll down and see that. Okay, so there's my surface plotted, and if I look at the point 0, 0, 0, we see that the surface has become degenerate now, because actually it's not clear. There's this negative surface and this positive surface, and they're intersecting there at a point which has really zero local area, right? Because it's almost like a singularity, so to speak. So it turns out that this surface created from the level surface of this function restricted to 0 is the double cone, and if we decide to increase our value away from 0, and perhaps grab something like c equals 1, then the surface is going to widen, right? So the idea is that the z direction is the special direction. If I increase my value for c, I'm going to basically take this point that's degenerate, and I'm actually going to spread it out, widen it out, so it's no longer reduced to a single point. And there you can see that. And this is why we call it a hyperboloid, because if you go ahead and trace these these curves that describe the boundary, unlike being a parabola, like in our paraboloid, the curves that describe the boundary are now hyperbolas. That's why we call it hyperboloid. And we can actually modify the value of c from being a positive number, where we were widening the cone, to a negative number. We're going to make the cone skinnier than a distance of 0 at 0. And that's going to look interesting, right? So what would happen if we made the cone skinnier? At 0, we're actually going to cut the cone off early, and then we'll recover kind of a paraboloid with the parabola pointing in the other direction, right? So now my hyperboloid with the hyperbola pointing in the other direction. Okay, so this is a fun example. It's called the torus, and in mathematics, this torus is a very special word. It means mathematical donut. And by that, we're thinking of the object which looks like a donut, but we're describing it mathematically. So, or a bagel, if you like bagels better. So here's a specific, so forget about the right-hand side here, forget about the 3/2, but if we look at the left-hand side, z squared plus 3 minus root x squared plus y squared quantity squared, if I made this right-hand side a function, called that f of x, y, z, now I have a scalar field in x, y, and z. And I'm going to restrict that scalar field to the specific constant value 3/2. And so then we're going to gain a level surface in 3 dimensions. And these were just some good constants chosen so that we get a beautiful looking donut. This would be a fun one to plot on Wolfram, so you can play around with it in multiple dimensions as you click and drag. Okay, so I mean, there's not a huge amount of math going on here. If we're ever going to graph these, we're going to do it on Wolfram. But we want to now, we're going to transition kind of into something slightly more important, which does contain math. And these are the normal vectors to implicit surfaces. So you would recall that when we were computing gradients and level curves, we'll write this down. When computing gradients and level curves, the gradient always described the normal vector to the level curve. right? In some sense, if I place a ball on a hill, the direction the ball rolls in will always be perpendicular to the direction in which the hill stays flat or constant, right? The ball will always roll downhill, which will always be exactly perpendicular to the direction with which the hill stays constant. So if I roll a ball and I decide to walk perpendicular to where the ball rolled initially, then my height won't change. That's something to keep in mind. So we're going to get the same thing here with normal vectors to implicit surfaces. We're just going to calculate the normal vector by way of the gradient, right? So, but we're going to give the normal vector a very special name. It's going to be n hat. Okay, so n hat is a vector which is normal to this particular surface at the point x, y, z. And that's just calculated with the gradient. If we want it to be a unit vector, obviously we divide by the magnitude of the gradient. I won't cover this piece right now. This is somewhat equivalent to our arc length formula, except we're adding this 1 in the third dimension. And the 1 is basically what's going to give us a little bit of a surface calculation instead of an arc length calculation. But you'll notice at the bottom we're covering this much more in depth later, so don't worry too much about it now. Okay, so if we want to calculate the surface normal to a unit sphere, we have our scalar function here. If we look on the side there, we restrict there, that's a scalar function, or a scalar field. And if instead we restrict to this side, this is our level surface. Okay, so the way I can calculate the normal to the level surface is by calculating the gradient of the scalar field. And I know you're all very well versed in gradients now. The gradient of this scalar field will be 2x, 2y, 2z. And we also need the magnitude of the gradient, which is very easy to calculate just as our standard magnitude of vectors works. And since we have, there's a slight typo here, since we have particular on this level curve, so on our specific level surface, we have the nice property x squared plus y squared plus z squared is 1. It turns out that this 2 times the root of x squared plus y squared plus z squared can be replaced with 2 times 1, right? Because x squared plus y squared plus z squared is 1. And so we recover that the gradient, the magnitude of the gradient, no matter where we are on this surface, right? We're restricting ourselves to the surface, but the magnitude there is equal to 2. So now I take the gradient of f, which was 2x, 2y, 2z, and I divide it by the magnitude, I recover x, y, z. Let's think about this a little bit by drawing. I should recall my level surface was the sphere. I recall this is just the surface of the sphere. So there's my level surface. If I draw the vector x, y, z, the vector x, y, z looks exactly like this, depending on where it's pointing, and it'll always point outward normal from the surface. Okay. We have one nice extra theorem here that's called the implicit function theorem. And that's very nice because it says that, okay, surfaces, let's reinterpret what this is actually saying. It has a lot of math words there. What this is saying is that surfaces which are not degenerate, as in, the gradient of f is not equal to 0 at some point on the surface. So as long as the surface is not degenerate, then it has a collection of explicit definitions. Okay, so recall the difference between my implicit. Implicit was something like f of x, y equals a constant. Explicit was something like, if I can spell, y equals g of x. Okay, so if the gradient of f is non-zero, then I can at least find a collection. I can't necessarily get the entire surface as one explicit function, but I can get a collection of explicit functions. Okay, that means a collection of functions which can be solved for either of the two variables. So let's just say solving for y. I can get a collection of functions which I solve for y, which together, when I combine the whole collection together, gives me the whole surface. So what's a really nice example of this? If we think about our unit circle, then note the gradient here, which would be 2x, 2y, is not equal to 0 for any x, y on the unit circle. Now what the implicit function theorem says is that hence the collection y equals root 1 minus x squared, y equals negative root 1 minus x squared exists, which together describe the unit circle. Right, this first explicit function, I've solved my function x squared plus y squared equals 1. I've solved it for y, so this is explicit. And this first one describes the upper half circle. The bottom one with the negative sign describes the lower half circle. And so when you combine them, we recover the full circle, x squared plus y squared equals 1. So I'm not going to actually read this whole thing for you, but that's the way you want to think about it, is that as long as it's not, my surface is not degenerate in the sense that the gradient is non-zero, you can always solve it for a collection of x's and, well, explicit functions. All right, that's all I have for you today. I'll see you in class. Bye.